Courtney Billing. I'm a member of the External Relations team, and it is my pleasure to introduce Dr. Emad Ebbini, who will be speaking to you today. Dr. Ebbini received his PhD from the University of Illinois at Urbana-Champaign in 1990. His research interests are in signal and array processing with applications to medical ultrasound. He is a fellow of the IEEE and has been active in several IEEE societies, conferences, and journals. He also served as the president of the International Society for Therapy with Ultrasound. Dr. Ebbini pioneered the concept of dual-mode ultrasound array systems for image-guided surgery. His research team at Minnesota recently demonstrated this technology, which is currently licensed for use in the treatment of peripheral vascular disease. They are currently investigating a number of novel approaches involving 3D imaging, non-invasive temperature imaging, and self-focusing arrays in the presence of strongly scattering objects. Professor Ebbini is passionate about improving the engineering design experience for our undergraduate and graduate students, especially real-time signal processing design. Please welcome Dr. Ebbini.
Thank you very much, Courtney and Anastasia, for the introduction. And it's a real. I'm sorry. Oh, sorry. Okay. All right. I'll do my best to project this. I think it's on. Are we okay? Well, I can. Very good. Better. Okay, I also known to be able to speak loud. All right. It's my honor to join you today and address this group. I'd like to share with you some of the fun things that we've been doing here for the last few years, and especially the concept of dual mode ultrasound arrays. And this is a technique that really was something we dreamt or had a vision to have almost 20 years ago now. And it required some technologies, both on the electrical engineering side as well as transducer technology, to allow us to finally apply this concept. We're currently in a preclinical stage of demonstrating it, and we're looking forward for collaborations that will allow us to use this in the clinic in the near future. So the promise of this technology is, as the title implies, it's a bloodless surgery. It's a way to intervene and destroy tissue, perhaps tumors and so on, without incision, without opening the patient body. And that's something is done with a non-ionizing radiation, so it can be done as needed. If not for complete cure, you can at least use it for palliative treatment and so on. So it has a lot of potential advantages. And hopefully I'll give you a sense of how this technology is going to be utilized, both primarily based on our preclinical work. But so obviously this is not just my work. There are a lot of people who have contributed to this, many of my former students and the current students in the lab, as well as collaborators at the University of Minnesota and other institutions. And obviously we received some funding from NIH and other organizations, including the university itself here. So just to give you a sense of how focused ultrasound works by a picture, there's a nice physics behind how ultrasound works, but typically, ultrasound transducers have shapes like this. It's like a lens of some sort, but it directs the ultrasound energy, and you're able to focus the energy to small spots like this whitish region. If you can hopefully see like the cigar shape, this is like a grain of rice. And basically the energy is going through the tissue up to that point, and this whitish region is actually ablated. It's killed tissue. And this happens in a very localized manner, and all the intervening tissue is saved. So no need for incision. You don't have to cut into the patient. But if you know your target, or if you can visualize your target, you can actually ablate that tissue and perform this without incision, without. Yes?
Why does it stop there at the green?
that's actually where it starts, and then so you start burning the tissue at this point, and it actually grows towards the transducer. By the way, I'd like to have questions as we go. It will be great because there are a lot of things that I'm potentially hiding, but I'm more than happy to explain. Hiding in the sense of trying to save you some of the detail, right? So, but if there are questions as we go, that will help us keep everything, and that, yes.
I'm still having trouble hearing you when
Yes.
you turn your head the other way.
I see.
I don't pick up if you put
Put on
the
your tie.
mic on your tie.
Very good. I'll try. Better? Excellent. Yes.
What frequency range?
Excellent. Yeah. Very good. So ultrasound, medical ultrasound is used in okay, that's too much. Better. Okay. We are working in the range of about 1 megahertz, about 10 megahertz. The higher the frequency, the finer that spot that we're talking about. It can become smaller, so you have better resolution. But your ability to penetrate deep is reduced because of the higher attenuation. So depending on the target, you can decide on the size of the transducer as well as the frequency to match the detail. This is a high precision surgery. You can go sub-millimeter. So the higher the frequency, but typically it's between 1 and 10 megahertz. Most of the data I'm going to show is at about 3.5 megahertz. It's designed for peripheral vascular disease. So the choice of the frequency, or the frequency, is usually decided based on the application, the target region, and how fine a grain of rice or sesame seed that you'd like to paint with.
The wavelength
Yeah.
is very small. And
Exactly.
fits that.
Excellent. Yep, the ultrasound in tissue, the speed of sound is 1500 meter per second. So for example, if you're working at 1 megahertz, that's 1.5 megahertz. That defines the width of this small spot. It's about a wavelength. So you get it exactly right. It's the wave. It's very nice, well understood physics phenomenon. As somebody pointed out, what are these bars? This is where you can predict where the lesion starts. And then it actually grows towards the transducer. And our contribution to this field is we have introduced this dual mode array concept that allows us to track and actually control exactly the size of this in real time with millisecond or sub-millisecond resolution. That's our unique contribution to this area. There is a lot of electrical engineering behind this, but it's applied for a good cause, I hope. Yes?
What's your max depth? Is there a
Yeah.
depth constraint?
So if, let's say I'm dealing with liver, I need to go about 15 to 20 centimeters. My frequency will be in the 1 to 1.5 megahertz. If I'm using like targeting the carotid artery, I can work with in the 4 to 5 megahertz range. And so it depends on the depth. Usually, the shallower, the higher the frequency I can use, the more precise I can be. And more, yes.
What would this particular illustration
Yeah.
show? I mean, what is the problem? What
Yes.
are you trying to-
So, for example, suppose there is a tumor in this region. So you can, a cancer tumor. So you can actually destroy the cancer cells here while saving all the intervening tissue without cutting into the patient. And this is done with non-radiation. It's not a radiosurgery, it's not radiation therapy. So we're not dose limited. We can actually do this as many times the patient would need it.
I thought the title had something to do with dual
Yep.
ultrasound.
Yep.
When do they come into effect? Dual.
Yeah, dual is I alternate between imaging and therapy almost instantaneously. That's what's unique about what we do at Minnesota.
Ultrasounds meeting.
It is actually multiple elements. So there is a lot of ultrasounds coming from many directions. But I am alternate. The duality is dual between imaging and therapy. So I'm able to see precisely what I'm doing. And that's unique to what we do. This is only here at Minnesota.
Multiple
Yep.
beams are then focused on that
Yep, yep. It's exactly. It's constructive interference. So we do my work at Illinois started by optimizing what we call multiple focus patterns. I can not only focus at one point, but at multiple points simultaneously in an optimal manner. If there are like obstacles, like bones in the case of the liver, I can go around them. And it's all enabled by imaging feedback. That's the dual mode array concept where it comes so important.
What happens to the tissue that's leaving?
Excellent, yeah. So,
Can you repeat the question?
yes, excellent. So the question is, what happens to the tissue that you destroy with ultrasound? That's an excellent question. So if the lesion is very small, like these ones, it will get resorbed. The body and by the healthy tissue, and it's like you pricked your finger. After a while, now if it's a larger lesion, the body will recognize this is too much to try to resorb, and so it actually becomes a scar tissue, but it's not doing anything. So if it's a tumor, it's no longer dangerous. Yep, it's benign. Yes.
Is it as well defined as you show it there? Those green,
Yeah.
they are that well defined
So
in the image.
okay, this is one cheating part. So, so this is nice homogeneous tissue. This is a nice piece of liver. It's very homogeneous, right? No, this is why our work is significant, because life is not always that easy,
Yes.
right? So actually, our system allows us to go through very distorting structures, like the skull. I'm going to show examples of that. So that's where the dual mode becomes so important. So the cheating part here is that I'm showing you a very simple case where everything is nice and predictable. The challenge is, can you always do that? That's where dual mode arrays come into play. One or two. I think it's good.
Has it been tried in animals?
Yeah. And not only in animals, it's also in the clinic. But this system that I'm going to show you is unique. It's hopefully a transformation in the sense of giving this as a prescription. We will be able to control the energy spatially and temporally with high precision so that the doctor can write this as a prescription. I want this much energy to go to a specific target. That's, yes?
Are you limited by size?
Yep. Everything is within, it's all engineering, right? So if I know my target, usually there is something we call acoustical window where I have high efficiency of transmission and so on. So I have to take all of these things into account in designing the applicator, right? So the size of the tumor, the depth of the tumor, all of these are factors in designing the applicator. This is, again, a simplistic situation just to demonstrate the ultimate promise of this technology, but then you have to do a lot of engineering to make this work. Okay, so next slide. All right. So if I have larger volume, because these are small, you know, a typical tumor, when you're ready to intervene, maybe 2-3 centimeters, even much larger. So you need to scan these volumetrically. And in the case of thermal ablation, there is what we call dose buildup. That is, there is a certain thermal dose that causes damage in this small region. But, you know, the energy still, there is some energy density that's finite in the region before the focus or the prefocal region. So as you scan more of these, you can actually start to build up and create collateral damage somewhere else. That's why imaging is required for guiding the treatment so that you can visualize your target, but also to monitor what happens. And we have developed a number of tools to allow us to do both. That's what I hope to demonstrate today. Yes?
Secure the patient in some way so they don't move during the process?
Yeah, ideally they would cooperate, but ultrasound is the best modality in the sense because we do real-time imaging at high frame rates. We at least have the potential of being able to track that motion in real time. That's one big advantage of ultrasound. So ultrasound as an energy modality is unique in the sense that you are able to localize the effect at depth and also the real-time imaging capability. MR, or magnetic resonance, is also an image-guided modality, but it's usually much slower than ultrasound. So with MR, they ask the patient, please, hold your breath, or do this, or do that. With ultrasound, we can track a lot of these things and account for them. Yes?
They don't need to be anesthetized then?
In principles, they don't need to. Yep, in principle, they don't need to. And actually, that's true because inside the body, these burns, there is no sensors, there are no nerves that would... so as long as you're not hitting these regions, right, the patient does not really suffer from, significant amount of pain because there is no nerve sensors. Yes?
Is there a heat buildup at the site?
Yep, it's possible. That's why we need to monitor. So, for example, let me go to the next slide here. So this is a prostate situation. There are clinical systems for the prostate cancer treatment. They use a transrectal ultrasound transducer like this. And it builds up a volumetric lesion, like this one, by raster scanning these individual grains of rice that we're talking about. Okay? And, of course, there is the potential that you build up heating in the prefocal region if you don't have the feedback. So if you have the feedback, you can avoid that buildup. And so usually they do this by timing the time between these shots, allowing the temperature, things to cool down before they take the next shot and so on. With our technique, I'll show you an example. We can actually keep going because we get feedback that allows us to know what's the baseline temperature. I just build on it. I don't give too much energy as I do this. So there'll be an example. Yes?
How the imaging process
Yes.
works.
Ultrasound is a ranging modality. So it's like a pitch catch technique. You send a pulse in a given direction and you listen to the echoes coming from that direction.
That's the imaging?
That's the imaging part. It's as simple as that. Like radar. Like radar. Yeah. Uh-huh.
Yeah.
Excellent. I like all of these questions and I'm happy to.
They
Yeah.
do this now, don't they, with kidney stones?
Yep. Lithotripsy. Lithotripsy, it can be done by actually using kind of a large reflector and it kind of gets focused on the stone. Lithotripsy is one of the most successful therapeutic ultrasound techniques. And interestingly enough, after some almost 40 years now of its introduction, the very first system is still probably the most effective system. So, yes?
Can I get rid of fat in coronary arteries with this?
You can go through all soft tissue with ultrasound, no problem. But you bring in a very important point. The tissue heterogeneity, the speed of sound is not the same. So now this is where the beam distortion can occur and you can start losing that precision that we're talking about. That's where the feedback and the corrections become so important. Bone is the most significant obstacle for us, right? So if I'm trying to do a liver tumor, I have to find a way to avoid the ribs. Because if I hit them with ultrasound, they can be heated differentially and they can cause a lot of pain. So we have developed techniques to use the intercostals and just direct shape the energy so that it goes through the intercostals preferentially. Yes?
Is there a limit to the number of times that a patient can be treated with this?
That's an excellent point. So unlike radiation therapy, we can use this for palliative treatments as many times as the patient needs to debulk tumors and things like that. There is no dose limitation. This is non-ionizing radiation. So it can be used as many times as necessary. Yep. Excellent.
How does it differ from focused proton radiation?
It's very different in the sense that still with proton radiation is still radiation, but it is a very nice technique, I have to say. It's, proton is a very advanced, one of the most advanced methods, but it does not, this modality focuses the energy by coherent constructive interference at the different targets and so on. And with radiation therapy, it's still kind of the more of a straight line, which is an advantage in their case. But the only issue is the dose limitation with proton therapy. Even though it's true, it's more effective. As you know, it's very expensive right now. It's not very widely available. Another advantage of ultrasound, you can deploy this worldwide. It's very cheap, right? Whatever is happening at the ultrasound imaging, in the ultrasound imaging space can be applied in the therapy space. So that's a big advantage for this technique. Question?
The reflective beam tells you that there's too much heat damage.
Yep.
What is there in the reflected
beam? So one of the immediate things that happen at the tip of that focus, you actually create such intense changes in pressure or extreme changes in pressure and temperature that you create immediate boiling of tissue. And so that initial event becomes a big reflector. And so you see a huge change in the backscatter, in the integrated backscatter of the tissue. And that can be quantified.
What about the prefocal area?
In the prefocal, it's highly localized initially. And then, yes, if you use excessive dose, you can start to see this happening in the prefocal region. So I'm going to give an example, actually, of something that we have done at Minnesota to show this. Okay. One of the main motivations for our work is working in transcranial applications. So this is now when things become interesting, because the skull is a very highly distorting medium for ultrasound. So you cannot predict that the beam will be as nice as the ones that I showed you if it gets distorted through the skull. So our imaging allows us to image. The quality of the imaging here is not that great, but it's enough to show me the skull, and the beam will be something like this. In this particular, this is actually a realistic size at a 3.5 megahertz. This beam is about 500 micron wide by less than 2 millimeter in the axial direction. So it's smaller than a sesame seed. And what we do right now, our research on this project, is to take the reflectivity data from here to try to refocus the beam and improve the quality of the focus. And that's already happening. It's becoming in the lab. So the big advantage, again, this is a unique way. With the dual mode ultrasound, we have inherent registration between what we call imaging and therapy coordinate systems. So the way I form a focus, we call it beam forming. I have multiple elements like you see in here, and each element that signal is timed appropriately at each, so that they all meet at the desired target point. Now, if I have a distorting structure like the skull in this case, this is actually a real image from this rat in here. I can use this information to improve the quality of the focus at that point. Not only that, we have developed techniques for imaging temperature change at that location using ultrasound. So I can also tell the quality of my focus as I refocus this adaptively. And this happens at very high frame rates, 500 frames per second. So every 2 milliseconds, I'm able to make a correction. We have done this. We're interested in opening the blood-brain barrier using focused ultrasound. This is an example in a real animal where we actually did that using a controlled exposure of ultrasound for 16 seconds with a 4-degree temperature rise, sustained temperature rise. So actually this does not damage the tissues, but it creates an opening of the blood-brain barrier. So this allows you to administer certain drugs that are needed. As you know, the brain protects itself against a lot of drugs or viruses and so on. So we can make a transient opening the blood-brain barrier to allow doctors to administer whatever drugs that they need, and then it closes after some time. Yes?
What if the cancer is on a bone? Can you do anything about that?
Right now, there is actually a clinical device that does this. I'm sorry, I'll do that. So the question is, for bone cancer, can this technology be used? This becomes an easier application of the technology because, usually you have access to the tumor, you can see it. It's now used for palliative treatment And there is a clinical device that does this under MR guidance, magnetic resonance imaging guidance. And they don't hope to cure the tumor, but they can debulk it so that you can give the patient, better quality of life. Yep, that's an option, but it's not a cure.
Are any hospitals using this?
There is a group in Rome that actually that use. Yeah, there is an Italian doctor who's making a name for himself. Actually, the University of Virginia has a number of clinical trials going using different systems similar to this, but it has magnetic resonance imaging guidance. So usually for slower treatments and for larger targets, that system is being used. There are several systems in China, actually, that use this technology as well. There is a couple of French companies. So this technology is here to stay. Well, like I said, our contribution to this field is to try to create this high precision therapy. I like it to be a prescription therapy. So not a single erg of energy more than needed if we can. I'm exaggerating just a little. Okay. So this is in transcranial ultrasound. I'm going to actually give you, if we have time, a sense of what we do. One is transcranial focused ultrasound treatments for neurological disorders, and this is funded by the NIH. And the other is the use of focused ultrasound for targeting atherosclerosis and other neurovascular structures in peripheral vessels, like the carotid artery and the femoral artery. And to start with, I want to make sure that people know we did not invent this technology. Focused ultrasound, the focused ultrasound as a matter of principle was investigated since early in the 20th century. By the mid-1950s, the Fry brothers, Professor William Fry and his brother Frank Fry at the University of Illinois, actually this is the lab where I got my PhD, they developed a beautiful system, and they did craniotomy, so they removed the skull for cats and patients and so on, but they demonstrated that you can actually form very fine lesions inside the brain using focused ultrasound. Of course, there are others, Professor Lely at MIT and so on, so this was demonstrated actually for the treatment of Parkinson and so on. But the problem was no imaging, and so only the physicist or the engineer knew what was going on. So when they did clinical trials, the surgeons were not, comfortable with that. So the technology had to wait for another 30 or some years until we started to see some imaging. So the image guidance was the missing part. This is Professor Fry, and this is a beautiful marvel that they developed at the University of Illinois. It's actually a very precise system. It was controlled. This is usually you couple ultrasound using a water bag we call bolas. This is his brother, Frank Fry. So again, image guidance is the key, and that's why this system did not receive a lot of interest until some 40 years later. I think I addressed some of these issues. Again, when you go through the skull, it can be quite distorting. So the early solution was remove the skull, which for some surgeons that's not a big deal, right? Seriously, they don't think. Yeah. Well, actually, still a lot of procedures are like that. They just simply remove the skull and they have the patient awake and so on. But still, it's a big worry. You'll have to admit, right? So if we can do this, then this is much better, right? Do it without, so it's all non-invasive transcranial, and that's our objective. And so let me just move on to what we're doing. So we're interested in characterizing these dual mode arrays, in generating, guiding, and monitoring monitoring and controlling transcranial focused ultrasound in Vivo. And that's what I'd hope to show you today. So I'm not going to bother you with a lot of the detail, but I have some really talented students who built a very nice system. This is one of the things, these are technologies that we had to wait until they became available. graphic processing units and field programmable gate arrays that allow us to do a lot of things in real time, but from the data acquisition or data generation, data acquisition, and a lot of the processing on imaging and so on, so that we can apply this control in real time that we're talking about. And we have shown the ability of dual mode arrays based on this imaging feedback, refocusing around the ribs. I've done that in a number of years, but we also target vessel structures like the carotid, and also compensation for motion. This is all enabled by the fact that we're imaging simultaneously while delivering the therapy, but not only any imaging, we're imaging with the same device that performs the therapy. So the registration is exquisite. No other imaging guidance modality can make that claim. These are examples of one of our subjects. The MR image is always advantageous because it has much nicer soft tissue contrast, so you can see the brain tissue quite nicely. We don't see that with ultrasound, but we see the bone structures much better. So for us, that's kind of our landmarks. This is what allows us to guide the treatment. And also these kind of reflections is what allows us to refocus the beam to obtain or improve our accuracy in targeting brain tissue. This was an ex vivo experiment just to demonstrate what we do. So for example, there is a 50 micron wire in here going through the brain tissue, and our DMUA would be imaging from this side. And typically we image in two modes. One we call synthetic aperture. This is all radar. Synthetic aperture techniques are radar type imaging techniques that allows us to see more of the skull tissue and the base of the skull. And this is our wire target. This is a measure of the resolution of the system, which was demonstrated to be, as I mentioned, about 500 micron in the lateral direction and about 2 millimeter or less in the axial direction. This is another imaging mode we call single transmit focus. This is our monitoring and guide. And so this is for guidance, just to see our target and so on. This is for monitoring. So it does not look as good as this one, but in the direction of the beam, this is just as good. So this is the wire, and this is the part of the skull that actually interacts with the beam. So think of this mode as actually a useful diagnostic mode because it tells us what interacts with our therapy beam. So when I'm imaging, I'm using the same delays for the therapy beam, but at diagnostic level. So this actually tells me which part of the tissue is interacting with my beam. So if I'm going to do something bad, it's going to be in that region, right? I need to monitor this. So it's a very useful feedback to tell us what could be damage or collateral damage that can result from something like this. Yes?
You must be able to model how the blood cools tissue.
Excellent.
So you can say that I like this part and I
Yeah.
hate that part and I want this to go
Yep.
away and I want
Excellent.
that to stay.
So we work with fundamental models for heat transfer. In the case, we call it the Pini's bioheat equation that includes a perfusion term. And again, one advantage to what we do is that we can actually get Doppler information. If there is a thermally significant blood vessel, we can measure the blood flow and we can incorporate that in our modeling. We have a couple of papers on this from our study on doing atherosclerosis, targeting atherosclerosis. So yes, you can model that effect, but not only that, we can also get feedback to conform as a real-time measurement while you're performing the treatment. You can actually measure the blood flow and account for it. If not in real time, we can also account for it retrospectively, post-treatment. Right? We can tell the doctor how well this whole treatment went by making these measurements in real time. Yes?
Due to the criticalness of the energy and the time, do you use something like the Da Vinci system in the application, or how do you?
Right now we have our own motors. We have in the Netherlands, we have collaborators, our technology transfer. We built a system like the one that I'm talking about that's actually ready for clinical use, and they use a robotic arm. I have to say it's kind of one of these very heavy industrial robotic arms, so it can be made better. But right now we do have one with a robotic arm, just to give you an initial position of the transducer. Keep in mind that our arrays can change the beam electronically. So once I am in the right place, I don't have to make a lot of mechanical movements. The beam moves around the target region electronically, which is much easier and much more convenient for both the physician and the patient. And it also allows for truly real-time tracking of the target. There was a question regarding the motion and respiration and things like that. You can actually account for that with electronic focusing much faster than mechanical scanning. Question?
What size of the transducer, what material do you use to do all of that?
Excellent. So because we do imaging and therapy, we need high-quality transducers that have very little coupling between the elements, and they also have large bandwidth. So there is 1.3 composite type material. It's PZT, but it's also in 1.3 format. And there is a French company that specializes in making these. They call it piezo composite transducer. But we have other technologies on the market, like CMUTs, capacitive micro-machined ultrasound transducers. So there are now more than one technology that supports it. But all of my work is using piezo composites. Yes?
Do you have anything proprietary so far, what you're doing?
Yeah.
Good.
The university has licensed some of our patents already on this. That's where the technology transfer effort. We've patented the basic dual mode ultrasound idea with some of the supporting technology. And it's under this technology transfer that we're going for first in-human demonstration of the technology. Yes?
I have some bone spurs of arthritis in my knees. Will this work on bone spurs?
So with bone, it's a challenging medium to focus the energy in, but it's possible if it's very superficial. If it's deeper, we have to optimize it for this particular application. But in principle, ultrasound couples through bone. In fact, that's all of our transcranial work is based on that. So the only question is how precise are we going to be? What is the degree of precision? But in principle, we can target structures. Yes?
Eventually, you said this would be prescribed.
Yep.
Who would actually be doing this? Electronic technician or,
Yeah.
or somebody?
No, the hope is ultimately we simplified all of the complexity of the system. You can create some degree of abstraction for the physician. The physician needs to know what is the ultimate or the therapeutic endpoint. That's what they need to specify. They need to specify trajectory based on where we see the target is and a therapeutic endpoint. We deliver the energy. The system is capable, again, with the dual mode array, you're able to characterize everything that goes through your beam. And you can use that to model what is the right exposure. Not only that, because of our ability to correct very quickly, we can guarantee that the target will be damaged without excessive exposure. So, yeah.
Who's doing that, though?
Yeah, I'm sorry.
Oh, who's actually?
The system will do this.
It's all automated.
Yeah. So the doctor needs to authorize that you can shoot, or if the doctor sees something they don't like, they can interrupt the system and so on. But once the system gets its orders, it can just go through the trajectory and finish the procedure. I'm going to do something. I'm going to skip, if you don't mind. I'm going to show you something really, hopefully, cool. Okay. Let me go here. I mean, this is how it's supposed to be. This is not a conference meeting. I have to go through my 15 slides. So we're having fun. Andy Casper, one of our EE students, he kind of defected to BME for his PhD, but he got his bachelor's. But so this is a trajectory. The doctor says, I need this block M painted inside a piece of liver, right? And these are your marching orders. These are the points. So this is what happens. We do imaging, therapy, imaging, therapy, and so on. So baseline, and then therapy, and then, right? So you can do this with control or without control. And I'll show you what happens in both cases. So this is without control. So this is going from one point to the next. No adjustment. There is a prescribed dose for every shot, right, on my grid. And you start going from left to right, up, down. The green places are places where the lesion was kind of just fine, which is based on our initial calculation. Just to show you that when we start, we're not delivering excessive ultrasound. There's not a lot of buildup of dose. But the red areas are where you can start to see excessive dose. And here is the result. You can see the block M. Look at this region. We're burning holes. There's no feedback here. Every shot receives the same energy regardless, right? Here's feedback and control, of course. So there's the algorithm. So you can see that the block M, hopefully the right size. By the way, I was at Michigan before coming to Minnesota, so we used to joke the different kinds of block M's. So, yeah. So here's our block M with feedback control. Hopefully you can appreciate the difference. Nice. This is where I'm not using any excessive energy. I'm just giving the patient the prescription that was prescribed. That is, don't give more energy than you need to. Because as I move from here to here, there is some buildup, and I start to adjust based on that buildup. So the dose gets smaller, right, as I see regions that are already heated. Does that make sense? Yes? This is dual mode. So this is another situation. We did a lot of these experiments just to see, the probability of forming a lesion, because as you indicated, when the tissue is heterogeneous or things change, things will not go as you specify. That's why you need the feedback, right? And I hope I have. Yeah. So this is a very significant result. This tells me I can start below the threshold. There is a threshold. There is a nice, well-defined threshold for lesion formation, right? I can go below the threshold and quickly find the threshold and finish my treatment. So even if I didn't know the exact properties of the tissue, this kind of feedback allows me to see what's the right dose. I can be below the threshold, and then sustain and form these types of lesions like you see, nice and uniform. Similarly, I can be much higher than the threshold and quickly find my way down to the threshold. This is, again, the advantage of this immediate closed-loop control, immediate feedback. So I can be wrong by a certain amount, and yet quickly I can find the correct dose so that I don't overexpose the tumor in this case. Somebody asked about prefocal heating. Here is the no control case. The energy is coming from here, uncontrolled ablation. This whole region has been ablated. This is the controlled case. This is part of the block M that I showed you. We cut right here, right, to show you the nice block M. This is just, if you're looking from the top, right? You can see that I'm only ablating about 1 centimeter, which is the extent of my focus in the axial direction. Does that make sense? So again, this is a prescription using closed loop control. Yes?
Now, for some heart conditions and atrial
Mhm.
could you do that on heart?
We have a patent since my Michigan days, but of course the technology is not here yet. But we plan to have a large aperture array that will focus at the moving heart, and because of ultrasound. So the idea, I can tell you, crossed my mind. This was patented back in 97, so just the patent just expired this year. And at the time, we actually relied on the mapping catheter to allow us to refocus the beam. Now I think we can do it better because we have this kind of feedback. At the time, the dual mode concept was not there, so we're actually relying on a transmit-only array. and the mapping catheter becomes like a refocusing hydrophone. But we can do it better with this technique. But that's, I have to say, this is like the next challenge for us, the three-dimensional imaging and therapy and so on. That takes another, leap in our abilities in terms of performing this. Yep. So this is another example of two different. So again, the transducer is sitting here, and we did this one first and this one second. And as you can see, there is no evidence of any buildup of temperature when you use the closed loop control. So this is the promise of this technique. Again, is prescription, what we call HIFO, or focused ultrasound. Just I do want to show you some of our transcranial work, especially the 3D imaging that enables this technology. This is Delonglu. Dr. Delonglu is my former student and postdoc, and he worked with us as a research assistant professor. He's back at Siemens now, but he's the main architect of the system, especially the software side. That enabled some of the things that I'm going to show you today. And so there is, in order for everything to work, you need to synchronize fully the operation of the array, transmitter and receiver, as well as a lot of the calculations that occur. And this is done on GPUs in a parallel architecture. I'm not going to bother you with a lot of detail. But we also do a closed loop control of temperature, and the temperature is obtained by ultrasound. You might ask, how is ultrasound sensitive to temperature? If you heat tissue, the speed of sound changes locally. So that's like the refractive index in optics. It changes, and we can detect small changes in the echolocations that are related to speed of sound, and also thermal expansion. So we have formulated this, and we have shown that we can actually image temperature change using focused ultrasound. MR can do similar things, but so this is an important form of feedback. But not only are we able to estimate temperature, but we also perform closed-loop control on that temperature information. And this is our piezo composite transducer. It has 64 elements in a linear array geometry, but it's the whole thing is a spherical structure so that you can get the high focusing gain that we need, these applications. And this is our subject, nicely sitting on a stereotactic unit. And they're under anesthesia, but that's just to keep them quiet. But so this is a typical experiment. This is how we start. Typically, we start by imaging in the back of the skull to see the occipital bone. That's a nice marker that we start with. And then we move to the desired target plane based on, atlases. They're like very nice, very detailed atlases for different sections of the brain based on these markers. And we design our exposure. And typically that allows us to put or place the focal spot to target a specific brain circuit that we need to. For example, we have 2 grants right now, one for treatment of epilepsy, where we're going to target the temporal lobe or parts of the temporal lobe to try to stop epilepsy seizure events using focused ultrasound. And so this is how we used to do it. First start from the occipital bone and find your target, and then you can deliver the therapy within the brain based on the brain atlases. More recently, I had discussion with Dr. Walter Lowe, and he was starting to tell us about the suture lines in the brain and so on. So I said, okay, we'll try to see if we can image those with ultrasound. So we did some 3D imaging of the brain. Here is a typical ultrasound image, nothing to write home about. Clearly, just, if you say so, right? If I tell you this is the skull and this is a scalp and so on, you say, okay, yeah, you dream on. Okay. Look at this is what we call a C scan. So this is at some depth through this image. As we scan the skull from the back of the skull to the front, and you can see the suture lines. This is the medial, this is the bregma, this is the lambda. So this was very exciting for us because now we can do the experiment as many times as we need to. We can do this, find the bregma, and then go back to the treatment plane based on these. And this is actually an exteriorized skull. You can see those suture lines very clearly for this situation. So this 3D imaging is going to give us the opportunity to repeat the exposure so that we improve our repeatability. If a procedure requires multiple, as you know, there was a question, how many times can you apply it? We can apply it multiple times, and we can go find our way to the right location. So this is something that we have started doing in the last about 8 months now. And these are examples, like this is the actual array. Everything is to right scale. So the image is rendered in the same coordinate system as the array. I can use this information for computing the field, the exposure. A computational model can be informed by the imaging that I use in this case. And as you can see, I can see those suture lines so that actually confirms what we claimed earlier. We told you that the lateral resolution is on the order of 500 micron. Indeed, if you didn't have that resolution, you're not going to see these structures. So we can be very precise in imaging, modeling the whole region, and then delivering the therapy. We did a lot of experiments to calibrate our ultrasound thermography with the thermocouple measurements. So I'm going to save you a little bit of the detail here. We've done the comparison, and this is thermography, repeated measurement. As you can see, some of the variance bars and so on, just to show. For example, for one of these beams that I was talking about, this is at the focal point here. You can see the exponential rise and decay. Very nice, indicating temperature. This is all non-invasive, by the way. There is no thermocouple. This is ultrasound imaging the temperature change. And this is spatial and temporal. So you can see that the heated region is also nice and confined. Using this information, we have begun very recently in our effort to create prescription blood-brain barrier opening to control the temperature. So this is a real-time closed-loop temperature control at 500 frames per second. This is the heated region. Again, this is axial, temporal. For the duration of time, you can see the pulsation of the animal. You can see it in here. It's also here, not as nicely, but you can see the pulsation. So that's a big advantage for the high frame rate. If we didn't have the high frame rate, we would not be able to account for these pulsations. So we can capture them, and it's a simple problem in signal processing to filter those out so that you can actually try to estimate the true temperature. And again, this is the key, prescription. Everything's going to be controlled with high precision, both in time and in space. Not everything's complete, right? We still have some work to do, but this is not only a promise, this is actually being done on a weekly basis in our lab. So it's yes.
How difficult has it been for you to get NIH funding?
I may be one of the lucky ones. I've been with the NIH system for any number of years. Definitely when things got bad, like others, we may. But I'm not one of these people who have like one grant for 20 years with NIH, because usually people at hospitals and so on, for them that's kind of a career-defining experience you have. So I do what I like. So now I'm working on Transcranial. A couple of years ago, I was working on temperature imaging and so on. So I change, but it has been a fairly steady source of funding for us. We did not really have an issue of not getting. I've been getting continuous funding. When I came to Minnesota, I came with 2 NIH grants, and most of my time here with 2 grants. Right now there are 2. One is just expiring, but one just started. It's a larger one. So it has been reasonable for us. Yeah. And then also we have some industry support. There is a lot, but I know that maybe my time is up. And so I don't know if there are any additional questions. I just want to maybe show you sorry. Let me show you. This is an application we're currently working on. There is a tiny structure in the bifurcation area of the carotid called the carotid body. This is responsible for breathing and for hypertension and so on. We're actually targeting that structure, and we use imaging to do that. Again, the lung. If I can, I mean, again, these images, you may think of them as low quality, but the beauty of real-time imaging. So, for example, hopefully you can, oops, sorry. You can see the pulsating vessels. We can actually see this structure. So with the 3D imaging that I described, we can see exactly the bifurcation point and go and hit the tissue in that region. And it is going to be hopefully amazing. We need to do a lot more of this to make sure that this is safe, because there are a lot of neurovascular structures that could cause distress but if this works, then some hypertensive patients can be treated without having to open anything. This will be no anesthesia, a very simple technique with very little risk to the patient. Yes?
I had a cousin and a real good friend that had a young child with a tumor on the spine deal, and it's too close to do anything.
Yep.
Is
This is the promise. Yep. This is the promise of this technology. For people who are not candidate for resection, you have at least the hope with this technology that you can just damage what you need to damage with sparing everything else. So when everything is in place, these patients might have some options. Yep. That's what drives us. Yes?
What are the major technology development areas that you
Yeah. So my interest is in the signal processing and imaging side of this, because this is going to ultimately, my hope is that these images, right now you can see these kind of silly things, right? But my hope is to give you a stamp size image on top of that vessel that shows you all the anatomical features of your target vessel. So that's where a lot of our effort is now focused, to try to enhance the quality of these images. We now perform what we call adaptive imaging schemes with arbitrary waveform generation. Again, like very advanced radar systems. So the idea is to have much better imaging of these target locations. So the surgeon is not going to have to guess. Right now, we're telling them, you know the anatomy. I'm going to show you things that will convince you you're in the right place. My hope is that I can actually give you an image here that there will not be any question. They can see the target with exquisite detail. And actually more using the time direction. So most of the phased array work that we've done and others are based on what we call CW, just a simple narrow band. We have now broadband signal. So we're going to use the time axis in time reversal techniques and inverse filtering techniques. So that's what excites me about the next few years in this area. We're very close.
So you're a navigator.
In a way, yeah. Yeah. No, it really has been just something that we enjoyed. You mentioned the NIH. We have been able to attract enough funding over the last so that we can keep going. We also got some good support from the U, which is great. I mean, we got the long I was able to bring back by help from our former dean and Professor Cave, our associate dean. They actually put in some funds to bring him back, and that actually propelled a lot of what you see. So we also got some Minnesota Futures grants, so it has been fun. Yes?
Is there a limit on the size of a lesion that you can use to focus ultrasound on, either too small, too large?
Yeah, too small, you can make it as small as you want, because right now we can observe with millisecond precision. As soon as it starts, you can stop right away. As soon as, like when it's a single boiling point. The size, the larger, it's actually less of a challenge. The main thing when you have large lesions is not to overexpose in the prefocal. So I have actually shown, even from my thesis days, by shaping the beam, creating these multiple focus patterns, I can actually create destructive interference in the prefocal plane. So when I do it simultaneously, as opposed to this raster scan I can actually improve the protection of the prefocal. So I can have larger regions without having to worry about overexposing so that's also in the optimization of the excitation. We call it wavefront synthesis. So I actually shape the whole beam. It could be a single focus in one direction or in multiple foci simultaneously, and you can optimize in the prefocal zone. So yes, in terms of the maximum, it depends on the acoustic window, how much of an aperture that I can use. The larger the aperture, the better the resolution and the definition, and at the same time, the larger size, if I need a much larger size. Okay? Yes?
What is your background beyond physics and electrical engineering?
I was as hardcore electrical engineer as they can get. As I was getting I got my bachelor's from the University of Jordan, completely communications, and that was my only interest in the world. My dad died of cancer, kidney cancer. I got an offer from Illinois to work on arrays for hyperthermia cancer therapy. I thought that was interesting. Let me see. And that's where it started. So I had to learn what I had to learn, starting from age 21 or 22 on some of these things. And it has been fun. Yes?
All of these images that we're looking at, are you able to observe those on existing hardware, the flat panel?
This is real time. Yep, this is real time. This happens during the experiment as you watch these things. If I can play this. This is actually what you watch during the experiment. This is the lesion forming in axial temporal. And it's actually, the trajectory is about 6 points in here. You can't hear DeLong and I congratulating ourselves. But so we're happy with so this just goes on, and you're just watching, or the doctor is watching. You just authorize the procedure. So this is happening. We're not waiting. So that's what the future is now, part of the title. Very good. Yes?
The pulses are just longer or more intense than the raster?
Our pulses? So we tend to start at a higher intensity than we know as the threshold is. So that initiates that event. But then we can stop right away. And then as we move from one point to the next, we take into account what the tissue baseline is. So actually that reduces the time or drops the intensity. As you saw in my threshold demonstration, I start at much higher intensity and then I drop down to the threshold value, or I can do it the other way around. So you can, there is a nice dose actually relationship between intensity and time, and you can modify either one. It's actually I times square root of t for short exposures like this. So we actually observe that, and it's part of our closed loop control. So there's nice physics that now the trick is in the biology, right? Sometimes you do all the physics right and so on, but the body, like in the light of people who criticize animal models, what happens in the mouse is not like what happens in the human. So that is still the bigger puzzle. But to the extent that we can, we'd like to make sure the physics is doing what it's supposed to do. Yes? Thank you very much. Thank you very much.
Thank you.
Thank you.